this concept of digital mission engineering, we've got tool sets that talk to each other. So I think it makes it a lot more automated, and it reduces the opportunities for mistakes.
Very quickly, you can click a few buttons and you can stick up a notional but realistic version of your mission up there, from launch to orbit to whatever the mission you're going to do.
I don't think a lot of people truly understand how much engineering goes into that to make sure you can watch a full-length feature film in 4K.
If you can model that orbit realistically, now you know what all those thermal loads are. Now you can design the most sophisticated telescope in the history of mankind. There's almost 100 lunar missions planned in the next decade, right? There's so many things going on in space.
If you're listening right now, if you're watching this and you're like, I have an idea for a nanosat and I want to launch it, you can.
Hey everybody, my name is Josh Poley. I'm the Vice President of Marketing Media for LSAS Tech. I've been working with DME tools for about 25 years, and I'm here with Jim to talk about real quickly about some high-level DME stuff.
Awesome.
Jim?
Yeah, and I'm Jim Shaw, Managing Director of Fastway Engineering. We are a channel partner of ANSYS, so the whole ANSYS portfolio, including all the digital mission engineering tools that we're going to talk about today. We're based out of Chicago, Illinois.
I should have said that part too, Jim.
Yeah,
we're also a channel partner of ANSYS, specializing in the DME tools for North America.
All right, let's start with the first question. Intro to DME. Let's start with the basics. What is digital mission engineering, and why is it such a game changer for aerospace and defense?
So digital mission engineering is the systems of systems level analysis of aerospace and defense missions and platforms, right? So you're modeling all these different systems out there and their payloads, and you need to know how they interact with each other and what happens when they actually get out there in the real world. And this DME is the simulation to do that before they get out there in the real world, then you realize something that you hadn't planned for. So really there's a few main parts of DME, right? There's modeling platforms. So vehicles, meaning things like satellites, missiles, aircraft, boats, ground vehicles. Actually, LSAS, the name of our company, stands for Land, Sea, Air, and Space. And that is because, we focus on the DME tools. And so once you model these platforms and how they move through a realistic environment, then you model payloads on those platforms. And payloads can be electro-optical IR sensors, they can be radars, they can be communication antennas, communication systems. And then now you have both of those pieces, all these things are interacting with each other, and that's where the mission part comes in, right? Like, what are you trying to do with all these assets and these vehicles and their payloads, and how are they interacting? And that's sort of exactly what DME is figuring out all those interactions and what they mean for what you're trying to accomplish, which is called your design reference mission, right? So what's your goal? What mission are you trying to accomplish?
Yeah, and Josh's background, you're the more system mission level. I'm an old EOIR guy. I mean, I was the engineer at the desk that was receiving, okay, here's the mission profile. What is the worst case? So, the second half of the question here, which is why is it such a game changer for sort of the A&D market, I think is because before we maybe wouldn't have such a connection between the system or the mission down to, say, our LRU level, down to our electronic level, down to the trace, the signal. A lot of that was manual, right? A lot of that was, spreadsheets and requirements documents, right? But now with this concept of digital mission engineering, we've got tool sets that talk to each other. So I think it makes it a lot more automated, and it reduces the opportunities for mistakes and generally reduces the risk.
Okay. Question number 2. How does DME improve multi-domain operations from air systems and space missions to radar and geospatial analysis?
So DME really improves multi-domain operations because multi-domain operations requires communication, and it needs to be quick and it needs to be reliable, and all these different systems need to talk to each other to figure out what's going on. So that's exactly what DME does. You think of the real world, you design a satellite in a vacuum, and not the vacuum of space, but I mean, without thinking of it's trying to communicate to aircraft on the ground that might be flying low below terrain. There might be other lighting constraints. There might be local jamming. There's all these things that could affect your conditions in the real world that you would want to apply realistic simulation so that you can be prepared to make sure that your communications between all these different systems still works when you go and field it. So an example would be an airplane flying that has a payload looking for something on the ground, like wildfires or whatever. And then that airplane has a communication. So it has an EOIR sensor pointing down, but it also has a comm package pointing up for satellite relay. And then that satellite that it's talking to also has to talk back down to a ground station. So there's a lot of different hops here, and that system wouldn't work if those hops weren't connected. And that's what DME does. It helps you connect all those dots so that the multi-domain operations is possible.
The other thing that I think some people forget about, because I think the original application, Josh, would you say the original application was aerospace defense? Very
Absolutely.
much
Yep.
critical, mission critical sort of tool set. I think a lot of people forget now, right? When you go onto a commercial aircraft, okay, and you're flying down to Florida for a vacation, and you want to get on Wi-Fi, yeah, that requires the same level of engineering that, as quote unquote, we have been doing in A&D for decades, right?
Right.
But now we have these very commercial, very consumer type applications, and that is the fact that we all have a desire to be connected, no matter where we are, no matter what our altitude is, no matter how fast we're moving. And I don't think a lot of people truly understand how much engineering goes into that to make sure you can, watch a full length feature film in 4K when you're over
Right.
the Atlantic. There's quite a bit of engineering in the
Yeah.
background.
Absolutely. Yeah. And think of the new the big internet satellite constellations, right? It's the exact same thing that we're all going to be connected to very soon. There's a lot that goes into that. It's been a long time coming, and it's going to be fantastic.
One of the coolest aspects of DME is its ability to tie into structures, fluids, and electronics. Can you walk us through how this works in a real-world mission scenario?
Yeah, I mean, I can certainly start from the perspective of the design engineer or the analyst, right? So again, what we're doing is we're connecting in a very sort of parametric and live way our mission profile, our situation, orientation, relative distance, a line of sight to things like the sun, right? And so as a sort of a structures thermal guy, the first application I think of how this is important to integrate is I want to know, for example, the total thermal load that the worst case, for example, a particular electro-optical assembly might see, right? Because optics, for example, are hypersensitive to their temperature and their temperature profile. So we might say, hey, this EO assembly has to be on a structure, and the structure's mission profile looks like this. And so what we would usually have to do is say, okay, what's the worst case? And it's not easy to pick the worst case. It's hard to kind of just look at a piece of paper and say, okay, well, here's time, here's relation to the sun, here's a solar load, here's the power, dissipation of the electronics, and trying to combine that together. And so a lot of times what we end up doing is we end up just getting worst case scenario of everything, piling that on as a thermal requirement and designing to that. And so sort of the downfall of that, you end up over designing, right? And there's one
Mhm.
thing that we really don't have a lot of room to afford is to over design, because in the structures and thermal world, when we over design, it's heavy, right? And when it's too heavy, every ounce counts, right? So it changes the dynamics, it changes kinematics, and it changes the cost. Let's be honest, right? Every pound costs a certain dollar amount to take a ride up, right, to low Earth orbit. So I think one of the coolest aspects of getting it to tie in is that I don't have to do that math now. I don't need to sort of create overly conservative thermal environment. I can say, okay, at this point in the mission, this is the thermal load, analyze it. At this point in the mission, this is the thermal load, analyze it. And I actually have the DME tools and my power output for my electrical engineers. I have this combination of these mission profiles. I have them tell me what the worst case scenario is. That
Mhm.
way I'm not injecting in some overly conservative environment. So that, to me, that's the coolest thing. Again, from like a designer and analyst perspective.
Mhm. Yeah, that's great points, Jim. I want to answer that one with a real world example of tying in from the smallest level component level is put inside of a system, and then that system's put inside of another system, and then systems. It all builds up, and then analyzing all of that together through the pipeline is what DME helps to do in conjunction with the standard physics solver tools that Jim was talking about. And the real world example I'll give you is a very high profile, very hard engineering problem, which was the James Webb Space Telescope. So the James Webb Space Telescope has some very complicated optics and mechanics to make sure things function properly when they're up in space, and it's super cold, and then they're also trying to use very sensitive optics up there. And those things change, and those conditions are something that DME fed over so that they could design to them. And in the same tools, not only were the optics and the mechanics and the the sun blocking things designed, they also designed the trajectory itself. So going out, and James Webb has a non-trivial orbit as well. It's a complicated orbit to get into, and it's a complicated orbit to model. And if you can model that orbit realistically, now you know what all those thermal loads are. Now you can design the most sophisticated telescope in the history of mankind, because you can go from that component level all the way up to, well, now it's on station and it's trying to observe the universe. And you can do all of that with these tools. And that's pretty exciting, because that's a real breakthrough technology.
I mean, if you see the pictures that come off of James Webb, I mean, I don't know what other evidence you need, for those to understand how much sort of optical design and analysis needs to go in, but those images are ridiculous,
Yeah.
And it's very cool to see.
You mentioned that we can model an entire mission profile just by entering a future launch date. How does that work, and what makes it such a breakthrough?
The DME tools are unique in that they allow you to continually improve your design with respect to the fidelity, right? So very quickly you can click a few buttons and you can stick up a notional but realistic version of your mission up there, from launch to orbit to whatever the mission you're going to do going forward is. And that's idealized, but it's still realistic, and it's following some of the simple models. And then really when you need to, and you start incorporating some of those components like Jim was talking about, and now you have a better idea of how your mechanical structure is, or in an airplane, like how the fluid's going to work over the wings of your aircraft, you start adjusting your model to incorporate those and increasing the fidelity. So now you stick in a more realistic orbit propagator, and you more accurately define the shape of your body, and that limits where your payload is and where your payload can point and how quickly your payload can point and all those things. So it's this dialable ability to increase fidelity and start really simple with something that's ideal but realistic, and then turn it into something that's way more of a real engineering tool that you can use to inform those subsystems and design those as well.
Good stuff. LSAS is the leading expert in DME in North America. How does their expertise complement Fastway's, and what advantages does this partnership bring to both their customers?
Yeah, I can start with this one here. I mean, it's like the way that Josh just answered that question, right? I can't answer that question like Josh and his team can. So, what's really important nowadays is for an engineering company, aerospace company, to be able to surround themselves with experts, right? When you're a small team, for example, let's say it's a startup, you have to pick and choose who you hire, when, and how. And so I think that one of the strengths that we have at Fastway is we bring, decades of experience of designing avionics, EOIR, and electronics. I'll say electronics adjacent, right? So structures, fluids, cooling, and a lot of the multi-physics that we have around these EOIR assemblies, and we can bring that to the table to our customers, right? Whether it's services, training, or software. LSAS is sort of the other half of that coin, right? So you have to be modeling your mission. You have to be preparing for the environment and mapping that environment. And I know some of the companies that we talk to, they want to bring it in-house, and it's just like trying to design something from scratch. That's fine, but what I think a lot of companies, younger companies, need is help with the experience. LSAS has so much experience, right? Josh, decades of experience in the industry is example, not only in the tool set, right? Not only in sort of the STK, ODTK software that's in the DME portfolio, but just mission experience in the industry. And so, I'm super excited for this partnership, because the LSAS team and the Fastway team can work together to help companies. You need help in many cases, not only at the mission level, but down at the signal and the trace level as well. So I for one am super super excited about this. We've got some events coming up this year that we're going to work together so that we can get in front of our customers and provide a dual sort of value. I don't know, Josh, what you think about it.
Yeah, I'm super excited as well. And I think you make a great point, right? A lot of the small companies that are trying to keep everything in-house but they still need to grow, and they have a very innovative idea. Specifically, there's a lot of these in the space world right now, and they have some great ideas. And you wouldn't go write a word processor if you were going to write a paper about something, right? Your expertise is in writing that paper and writing that new story, that new white paper, whatever. So relying on Fastway and LSAS to give you the tools to solve those problems is very exciting, and it's extremely empowering for these small companies, because we have small business partnerships. People can get started with this, and between our two companies, we can get you started, get you going in the right way. The other thing is these tools that we support and train on and are experts in, is these are tools that solve so many problems at once, right? Like, everybody that's going through engineering school has written code that is like an orbit propagator if you are aerospace, or solves some of the stuff that you've done, and that's a very specific problem that you've done. So these small companies, sometimes when they set out, they like, well, we can solve all this in house, and that's true, and maybe it works for their first few customers, but then as they grow and they're like, well, we need to expand, and all these things that we didn't think of that we now have to account for in our systems, right? That's a hard place to be in. So developing from scratch can be a challenge once you start to grow, and relying on the expertise of people that have done it across broad areas of technology, they solve all the problems that you don't even know you have yet.
Yeah.
And you can grow into these spaces. Like, I'll give you an example of a systems toolkit, right? So there's a lot of different coordinate systems of how you keep track of where spacecraft are. And when you see these big programs, they have requirements for maybe 4 or 5 different ways of the data going in, being in these different coordinate systems. Well, SDK was designed outside of a program, and so it worked with those 4 or 5 coordinate systems, but it also worked with every other coordinate system, right? So it sounds simple, but it's not. And keeping track of all that stuff, that's kind of the promise of using tools that Fastway and LSAS support, is they're designed to solve every problem. And as these small engineering companies grow, there's all these areas where they might not have the experts that they need to grow into that area. And that's where our team is here to support. And that's going to be very exciting.
Yeah, it's like you don't know what you don't know.
Mm-hmm.
And why that's such a big deal now, right? Is it's not just 5 big primes going after big contracts and that's it, right? We've got a very healthy aerospace and defense market. When I say healthy, I mean we've got small and medium-sized enterprises that are entering the market, right? With SBIR and STTR grants, for example. So,
Mm-hmm.
There's a lot of opportunity. If you're listening right now, if you're watching this and you're like, I have an idea for a nanosat and I want to launch it, you can. I mean, we have the mechanisms in the marketplace to get you the resources you need, some of which are publicly available, like potentially funds, right, through grants, through DoD or NASA, and others are through partnerships like ours. So, yeah.
Josh, what's next for DME? Any upcoming innovations or developments we should be excited about?
I can't speak exactly for ANSYS, but I'll give you my thoughts on the trends I see that I think that it's going in this direction. So a lot of these new satellite companies and ideas are revolving around the idea of many satellites up there. So you've seen some of the additions to the DME tools over the last few years have been making that easier to design for in the software. So I think that they're going to be continuing to add features for these giant constellations of thousands of satellites, offering us all kinds of different services from space. And I think that is going to go hand in hand with more automation. And you see them already, ANSYS already starting to implement some more automation, and probably based on AI tools, right? Like, that's what everybody needs to do. And it's just exploding, like Jim was saying, to a level of, it's very healthy. There's tons of people doing it, and they're making tons of awesome stuff. And so I think the tools will evolve so that small groups can solve these big problems with many, many, many things up in space and many payloads, and also lunar, right? Like there's almost 100 lunar missions planned in the next decade, right? There's so many things going on in space, and you've seen ANSYS add specific capabilities since then, catering to the lunar crowd. So I'm sure that's going to happen with Mars as well, and that's all those things are pretty exciting to me. That the moon stuff, and then the number of satellites that are going to be up there, giving us these things like global internet, right? That's going to be fantastic, and there's going to be choices for global internet, and it's going to be great. It's going to be very, very connected time, so to speak.
Yeah, I see it sort of from the other side too, right? I really enjoy building out a workflow, right? Building out a tool set and helping designers, engineers connect tools together. We've been scripting and doing that sort of a manual way for quite some time. So I'm enjoying seeing this progression of the tools being very, very connected to each other, less mistakes by humans. You mentioned sort of AI, right? But the reality is we're trying to use software algorithms to fill the gaps where we don't have the data. Humans are really bad at making up data, right? We're really bad at plugging that gap. Statistical math, pretty good at it, right? So the other thing that's kind of happening too, right, is it's not just the physics, right? We're not just seeing this flow down from, say, mission level to physics, like structures, fluids, thermal, high frequency, RF. We're also seeing it connected to, for those that care, right, risk, revision management, right? Sort of this layer of process control that becomes more and more critical as you have a more and more complex system, right? So, data management systems, release tracking. I mean, these things are going to get very, very, very complex very, very quickly. They are complex. Let me say they are complex, but as the small and medium-sized enterprises start to build out new value and new solutions, those solutions start off as maybe a single point solution, and they turn into a system of systems, to use your term, Josh, very, very, very quickly. So, we're seeing it really embed into the sort of the model-based systems engineering sort of mantra. So for me, that's exciting because I like seeing new tools kind of talk to each other and automate. Just makes it easier for the designer.
Okay, last question for Josh. How and where can people learn more about LSAS?
To learn more about LSAS, you can go to our website, lsas-tech, tec.com. There's no H in tech. It's cut off. Or you can check us out on LinkedIn. And pretty soon we're going to be migrating over to lsastech.com, just so that I can say this a little bit easier without having such a confusing URL.
Good stuff.
Great. Yeah. Good stuff. Thank you, Josh.
Thank you.